Hello, welcome to Problem Solving with Mr. Anderson. We're going to look at assignment 2.1, problem number 7. Two identical uniform smooth spheres, each of weight W, rest as shown at the bottom of a fixed regular rectangular container. Find, in terms of W, the forces acting on the spheres by A, the container surfaces, and by B, by one another, if the line of centers of the spheres makes an angle of 45 degrees with the horizontal. Not a lot to go on, no numbers, but consider this to be sort of like marbles in a container. Just two marbles in a very small container. The object we know slightly more about, or at least have fewer unknowns, is going to be the top sphere. The top sphere is going to have its own weight, W. It's got a force upward at 45 degrees. I'm going to call that force 1, coming from this contact between the two objects. And because of the wall of the container, there is a force, I'm going to call that force 2, pointing to the left. So there's only 3 force vectors involved in that one, and there are more than that in the other sphere, as we will soon see. So I'm going to go with the one that has fewer unknowns. So since we're looking to find things in terms of W, and W is in the y direction, I'm going to start in the y direction. Never hurts to acknowledge that the sum of the forces in a given direction, well, in this case, equals 0. In the y direction, we've got F1 in the y direction, upward, positive, minus W, weight, equals 0. So just those two forces combined equals 0. So we've got the F1 in the y direction looking like that. And let's move on this a little bit. We got F1y equals W, move W to the other side. Now F1y, the y component, we are given that this angle is 45 degrees, so F1 times the sine of 45 equals W. So if I want to solve for F1, that's going to be W over the sine of 45 degrees, which works out to be about 1.4 times W. All right? So I've found one of these forces. In the x direction, the sum of the forces in the x direction are also 0. And in the x direction, we've got the x component of that first force. F1 in the x direction, and that's pointing to the right. F1 in the x direction minus F2 equals 0. That tells me F1 in the x direction equals force of 2. F1 in the x direction is going to be F1 times the cosine of 45 degrees equals F2, but I already know what F1 is. That's going to be 1.4 times the weight times the cosine of 45 degrees, which is about 0.707 equals F2, and it turns out that 1.4 and 0.707, well, pretty much cancel each other out. So force 2 is equal to the weight, equal in magnitude. Right, so we figured out the first sphere. The second sphere has its own weight, W. It has the left side of the container pushing to the right, so I'm going to call that force 3. I don't know what that is. Because of the contact between those two spheres, down and to the left, I had previously noted that as force number 1, and because of Newton's third law, the force that the bottom sphere exerts on the top sphere is equal in magnitude and opposite in direction to the top sphere's force exerted back on the bottom sphere. So magnitude-wise, that's going to be F1. And lastly, this container has a bottom, and so there has to be some upward force, which I will call force 4 upward on that lower sphere. Now, I know a little bit more about the left and right forces because I actually do know something about force 1. Otherwise, a lot of that stuff is a mystery. So I'm going to start in the x direction for this solution. Some of the forces in the x direction are 0. You probably don't need to say that first part. It's just good to acknowledge sometimes. But what you do need to say is basically the setup equation for this solution, which is to say F3 to the right minus F1 in the x direction equals 0. That part, I'm going to put a little star next to that. That one is really the setup. If you don't get that, then you're not getting this problem. And this is the example where the free body diagram is directly translating to your formulaic solution in the same way that this formula right here and this formula right here were directly pulled from the free body diagram. The forces that appear in the diagram are the very same ones that appear in your algebraic solution. So I cannot emphasize enough, having those formulas stated clearly is not only a good idea, it's actually necessary. Like in order to get all of the credit, that's basically the starting point for the solution for the rest of this. So F3 equals F1x, but earlier on we were informed that F1 is 1.4 times W. So that's 1.4 W. Oh, I should say, actually before I sub that in. F1 in the x direction, which is going to be x comes to the cosine of 45 degrees. And so then I'll sub this in. So we got 1.4 W times cosine of 45 degrees, which is about 0.707, which we saw earlier. That really cancels out. So F3 is equal in magnitude to W. And lastly, in the y direction, those forces are also 0. And in the y direction, this is the most involved part of the problem, really. So we've got F4 upward. We've got F1 in the y direction, downward. We've got the weight of that sphere itself downward. And those three forces all add up to 0. So F4 is going to equal, in magnitude, F1 in the y direction plus the weight of that sphere itself. F1y is going to be F1 times the sine of 45 degrees plus the weight. And that's going to be F1 again is 1.4 times W, 1.4 times W times the sine of, sine of 45, which is 0.707. Plus W, well, 1.4 and 0.707 cancel out, so that's W plus W equals F4. So I guess F4 equals 2W, which shouldn't really be a surprise, should it? Because while the walls of this container are stopping everything from falling out sideways, really, if you are the bottom of this container, you have the job of supporting two spheres, each of weight W. So yeah, that makes perfect sense. The force upward from the bottom of the container should be equal to the weight of the things that it's supporting. That's it. There you go.